Phase transitions are a central phenomenon in statistical physics and refer to a sudden change of behavior as some parameter of the model is changed. That means that configurations that correlate well on a microscopic scale may look radically different on a macroscopic scale, if they correspond to different sides of the phase transition. However, it's also possible for configurations that correlate well microscopically to behave different macroscopically, though they correspond to the same law. For instance, when one configuration is a small perturbation of the other. This has been studied thoroughly in planar percolation models. A formal framework in which questions like this could be studied was introduced in a seminal paper by Benjamini, and Schramm in 1999. Let omega be a string of zeros and ones chosen uniformly at random. Obtain an epsilon perturbation of omega by independently resampling each bit by probability epsilon. A sequence of Boolean functions is said to be noise sensitive if for every epsilon the functions evaluated at the two configurations are asymptotically uncorrelated. In planar percolation model, one is interested in long-range connections. A natural observable in this context is the horizontal crossing of a square. Benjamini, and Schramm show that square crossings in critical bond percolation is noise sensitive, meaning that having observed a crossing before the perturbation gives us no information asymptotically whether there will be one after the perturbation. For various disordered systems, polymer models and spatial growth models, the main observables are not Boolean but real-valued. In 2011, Benjamini proposed a natural approach to explore noise sensitivity of real-valued observables. His approach can be synthesized in the question, is being above the median a noise-sensitive property? In this paper, we present the first progress on Benjamini's problem. To each edge of the square lattice, toss a fair coin to determine whether to assign it a weight A or B, where A and B are non-negative real numbers. Let Tn denote the minimum weight sum picked up along any path from the origin to a point n steps to the right. The distribution of Tn is unknown, but it has a median. For large n, we expect the median to split the distribution roughly in half. Moreover, since the weight takes on only two values, the indicator function of the event that Tn is above its median is a Boolean function, and fits the framework above. Benjamini thus proposed to investigate whether this sequence of functions is noise sensitive. A heuristic argument based on KPC scaling indicates that Benjamini's question does have an affirmative answer. However, in order to present a rigorous theorem, we shall need to make two simplifications. First, we replace the point-to-point crossing time with the horizontal crossing time of a square. Second, we impose a restriction on the vertical fluctuation of admissible paths. More precisely, let alpha be less than 1 over 22 and fix any sequence kn such that kn grows no faster than n to the alpha. Let tau n denote the minimal weight sum among all paths crossing the n by n square horizontally and whose vertical fluctuation is at most kn. Our main result says that the sequence of indicator functions of the event that tau n is above its median is noise sensitive, and indeed splits the distribution of tau n roughly in half. Our method of proof will be to bound the influences of the individual edges. The influence of an edge is the probability that changing the value of that edge will change the outcome of the event that tau n is above its median. Since changing the value of an edge from A to B may affect tau n at most B minus A, and only if the edge is on the weight minimizing path pi, it follows that the influence is roughly the probability that the edge is on the geodesic pi, and the difference of tau n and the median is no more than B minus A. Since there are order n square edges, it will suffice to show that the maximal influence is of a smaller order than 1 over n. We will do that via a Cramér type moderate deviation estimate of the crossing time of an n by kn rectangle.